Thank you very much, Alex. And I'm really honored to be here and present Sanjeev Gupta today. I have some notes. So Sanjeev is a clastic sedimentologist at the Imperial, is interested in the paleoenvironmental evolution on planetary surfaces. His research is a little bit random and is easily distracted. These are his notes, not mine. I would never dare to say that. He enjoyed the French Alps as a PhD student, did a postdoc with John Underhill, which is another keynote speaker here, working on Sin Rift deposits in the Sinai Peninsula, which significantly involved hanging out at the Moon Beach Holiday Resort. I don't know if that is a real place. Is it? It is. Okay. I will. He has subsequently explored under the sea with sonars in the English Channel, looked at rivers associated with early civilizations in India, which led to a project on fluvial aquifers. He now helps look after 2 rovers on Mars. So please, let's welcome our keynote speaker, Prof. Gupta.
Thanks very much, Fulvio. Thank you for inviting me. It's really kind to be here and wonderful. So I have to tell a story. The last time I was in Dice, which is this village we're in, was when I was 19, and I was a summer intern for an energy company, and they sent me first class. I'd only been there for about 3 weeks on a plane to Dice, to the core sheds to log core when I know new sedimentology at all. And I hope nobody's ever used my core descriptions because they were awful, but that was a long time ago. And I also got to eat Scottish porridge. I hope you've had the experience of Scottish porridge. But it's salty, not sugary, and that was quite a shock. Okay, I'm going to take you to Mars, and this is a talk. So operating a rover is not just me, it's hundreds and hundreds of people. I'm going to talk about 2 different rovers, the Curiosity rover and the Perseverance rover, and both of those rovers have about 400 scientists and 200 engineers making the science happen. So it's really, I'm representing the team and giving you the highlights of what we've discovered. And both missions have just been marvelous for our field as sedimentology. And it's really exciting that Perseverance has collected samples of sedimentary rocks that will be the first sedimentary rocks away from Earth to come back to Earth, hopefully sometime in the 2030s. Very exciting for us all. So, moving on. And now here Okay, take some time to read this. This is a quote from an early astronomer in the 1870s, something like that. Henceforth, the globe of Mars should no longer be presented to us as a block of stone revolving in the midst of a void, in the sling of solar attraction like an inert, sterile, and inanimate mass, but we should see it as a living world, adorned with landscapes similar to those which charm us, in a terrestrial nature, which I hope to convince you of, a new world which no Columbus will ever reach. Well, maybe that's wrong, maybe we will reach it, but on which doubtless a human race now resides, works, thinks, and meditates as we do on the great and mysterious problems of nature. I think thus, at the moment, I'm going to disappoint you. I have no secrets to reveal here. But over 100 years ago, people genuinely believed there was an advanced civilization living on Mars, because why not? Nobody 100 years ago thought that we would ever reach Mars. And so next slide is a headline from the New York Times from 1911. And the New York Times is, it's not a tabloid, it's a major newspaper. I'll let you read that. So there's all the great Mars Canal controversy, but Lowell convinced people that there was an advanced civilization living on Mars, and they were building canals to transport water from the poles to the equator. So how wrong can you be? So that's a lesson, how wrong can I be, or we in our interpretations. So Mars was likely, sorry, I'm having problems with something here, just bear with me whilst I click something off.
Click it to your right as well.
No, there's something that's annoying that I'm trying to get rid of that I can't get rid of, nope. You'll have to bear with me. as I move through. There's an annoying NASA program that wants me to connect to them now. But Mars was once warm and wet, and we can see this from the orbital data, which shows evidence for rivers and lakes on the surface. And people have mapped the distribution of these, and you can see in the middle terrains, the orange highlands, that's high topography, where we see abundant evidence from orbital data of rivers, valley networks, paleo lakes and craters, etc. So Mars, in its early history, was wet. We don't know how wet, and we don't know how warm. And then that climate changed about 3.5 billion years ago, 3 billion years ago, sometime around then. So what happened? And really, you can't do that from orbital imagery. You really need the ground data to test how things change, to look at the sedimentology and look at the stratigraphy in detail, and that's what the rovers are doing. So we have two really detailed ground points, both from both Curiosity and Perseverance rover, and being able to do this. So Curiosity landed in Gale crater, and Gale is a 150-kilometer diameter crater, and what we can see here, I'm going to point over here, we have the catchments of the crater over here, and this fed drainages into the crater center, basically. And through Curiosity, we've been able to analyze how those sedimentary systems evolved downstream from the catchments themselves. We can actually see the paleo catchments preserved in the landscape because 3 billion years ago, the tap got turned off. So you can actually see a paleo channel or paleo valley, paleo channel preserved in the landscape, fossilized in the landscape, and that's a valley, a channel that's 3.5 billion years old, that transported water and sediments into the crater and built alluvial fans that fed into finer grain systems downstream. And I'm going to talk about that and talk about the stratigraphy. So Gale was chosen because in the center of the crater we have this mountain that's several kilometers high, Mount Sharp it's called, or Aeolis Mons, and that preserves that stratigraphic record, so we can basically drive up the stratigraphy. We're never going to reach the top, just in the lower foothills, and see that transition. One of the reasons that this Gale was chosen was that we saw transition from orbital spectrometers from minerals that suggested there were clay minerals at the base into sulfates, and that suggested that there was a drying up sequence. But we didn't know what that actually represented in terms of the rocks, and that's one of the things we've been trying to look at. So this is just a summary. You don't need to take this in. It's just showing you overall the different formations we've mapped out and designated, and the change, and we've reconstructed a stratigraphic column in enormous detail as to how that stratigraphy changes through time. And I'm going to run through that very, very quickly. So at the base, we actually see fluvial conglomerates. You can see some examples here in some fluvial channels, which represent what we think are the oldest stratigraphy. Obviously, with Mars, there are different interpretations, and some people actually think these rocks are the youngest stratigraphy, not the oldest stratigraphy, and it's just because we're really limited as to where the rover can go to and what we actually have and what marker beds we have, usually none, to be able to track things. Obviously, what would be lovely is to have some fossils to help us with some biostratigraphy, but obviously if we found fossils, nobody would be interested in the sediments at all. So, thank heavens we haven't found any fossils yet. Sorry about this. This is a silly program that I can do nothing about. So here is Gale crater, 150 kilometers in diameter. I'm going the wrong way now. I can't do anything about that. You're going to get a lot of blinking. Okay, so here's an example of a beautiful mosaic. This is at a site called Kimberley, where we can see these lovely fluvial sandstones that are dipping down towards the center of the crater, and you can see Mount Sharp in its glory in the center. And we made a prediction when we saw these fluvial sandstones, fluvial deltaic sandstones, we made a prediction that downstream the water would have to pond in the center of the crater, and we would discover lake deposits, which are what astrobiologists think of as our highest priority rocks or environments to search for evidence for ancient life. And lo and behold, we got there. We came to a place called Pahrump Hills. It's named after a place in Nevada. You don't want to go to the real Pahrump Hills. The one in Mars is much better. Apologies to anyone from Pahrump Hills. It's full of casinos in Pahrump Hills, no casinos yet on Mars. And you can see those beautiful light-toned rocks, and from this distance we had no idea what those rocks were, but when we got up close and personal, we could see these beautiful rocks with these lovely millimeter-scale laminations that are 1 or 2 millimeters, and the grain size of these is below the resolution of the cameras, so the grain size is below 60 microns, and we're using a hand lens camera that's at the end of the arm, the Marley camera, to look at this. So the interpretation of these, and most people accept this interpretation, these are lake deposits, and these are the deposits from river plumes entering the lake and depositing out of suspension to build up these layers. There is an alternative interpretation that these are actually lowest deposits, airfall deposits. It's difficult to explain how you get those laminations in airfall deposits, but this is Mars. And I think the important thing with Mars is to always be wary of the alternative interpretations, because we can't actually physically look at the rocks. We can't examine every single aspect. Every single site we go to could be a PhD project, and we just have to keep moving on. So one of the reasons to interpret these as lake deposits is that inset within these, we see these beautiful lenses. You can see whale rock over there and newspaper rock. And these are little lenses of sandstones interstratified within those laminated mudstones, which contain cross-bedding, beautiful cross-bedding. And those are interpreted as fluvial channels that entered the lake and have been preserved here. And right at the top, we can see a rock called Salisbury Peak, which is planar laminated sandstones. We couldn't drive up to it, unfortunately, so we couldn't get a handle on the grain size, etc. But again, that's interpreted as a top of a coarsening up succession. And above that, we go back into laminated mudstones. And we've driven through hundreds of meters of laminated mudstones. It actually got rather boring after a while. Chris, sorry. Because I like sandstones. What it means is that these lake deposits lasted for a long time on Mars, and they represent sustained standing water on Mars. We see no evidence for ice-covered lakes, no evidence for dropstones or anything like that in these deposits, so these were open water lakes that existed for hundreds of thousands, if not millions of years. So, oops. Oh, dear. So this idea of lake cycles, lakes developed, they dried up, they developed again. There's one example of mud cracks, putative mud cracks possibly, but we've only seen one really clear example. And then we see quite complex variations. So this is some work by a student of Chris Feddo's over there, who's documented cross-bedding within the lake deposits. So we see lake margin deposits. It's quite subtle, quite difficult to tease out, but certainly these environments show subtle changes in that lake environment, which are beautiful to document. And then we get up into more lake deposits. We get into this beautiful Pettigrove Point member. So I just want to show you some more of these beautiful laminations. You can see these millimeter scale laminations, beautifully preserved. And then within Jezero member, note the Scottish names, which I'll explain very shortly. You see these crystal molds, possibly gypsum crystals that have grown within the sediments themselves. And then finally, we got to a place that we named Glentorridon, after Glentorridon in Scotland. And essentially what happened here, so this was the most clay-bearing unit, so to explain these Scottish names, we don't name the rocks we analyze or look at by numbers because it's easy to make mistakes, so we have quad names. And when we got to the area of Glentorridon, we didn't have a name for that quad, so I suggested Torridon, just because of the fantastic geology in northwest Scotland, and it was accepted, but we ended up spending about 2 years in this quad. So we have literally hundreds and hundreds of rocks on Mars named after Scottish place names. So these are all the Scottish names on our trajectory over here, but when my postdoc, Steve, mapped these onto Google Earth map, and you can see these are all places in Scotland that have an identical rock on Mars. When I drive around Scotland, I know nothing about the place, but I actually know what that rock is. So this is Aberdeen. It doesn't look very exciting, I'm afraid. I'm afraid Glasgow got a drill hole. Sorry, Aberdeen. And even the place we're sitting at has a name on Mars, a rock on Mars. This is Dice. with these beautiful laminations over here. So this is a ChemCam RMI, so there you go. Scotland lives on Mars. So, and then right at that top of that succession, we see a transition from the lake deposits into beautiful cross-stratified fluvial deposits of the Knockfarrell Hill member. And Chris has got this beautiful slide here just showing you the evolution of the environments that have been reconstructed from those things. So a 3D model just showing you how those environments have changed. There's probably things that are not quite right about this, etc. We can only do 20% of that, but you get a sense of that. Then above this succession, we see a dramatic change from clay-bearing rocks that are these lacustrine deposits into a succession that from orbit showed sulfate signatures in the geochemistry, but we didn't know what the rocks were. And it was hypothesized that this was a large-scale drying out of this site at Gale Crater. Planetary scientists tend to get a bit carried away. They see one thing in one place and then infer that for the entire planet. So this was seen as a global drying out of Mars on one data point. And so it's very useful to have sedimentologists on the missions to try and constrain people. But here we see in the lower part of that face, we see clay-bearing strata. These are lacustrine deposits. And we see a transition into these sulfates, which are thought to be a dry gale. And the rocks here are just beautiful. You can see the landscapes are incredible. And what it turns out is most of the rocks that we see are actually aeolian deposits there. So that drying out is true in this thing. We see beautiful aeolian, large-scale trough cross-stratified sandstones indicating the migration of large-scale dunes. And so in the lower part of the succession, we see this abrupt drying out that we don't really understand at the moment. And we really need to take apart that data in more detail. But then it's not a unimodal or transition. Within that succession, we actually see some lenses. You can see some dark lenses. You can see the arrow that says prow lens. We see some dark lenses that are coarser-grained sandstones within that, and we just see spectacular sedimentary structures in here. So here's a unit just showing some large-scale trough cross-bedding. I don't know whether you can see that. And here's one of the lenses over here. It's only about 70 centimeters thick, inset within trough cross-stratified fine sandstones. And if we zoom in detail, what we can see is at the lower part we see planar cross-bedding, and the upper part we see these beautiful ripple cross-laminated sandstones. But the ripple cross-laminations are basically symmetrical ripples, basically. So what we're seeing here is beautifully preserved wave ripples, and this is the first time we saw wave ripples on Mars. So you can see here another example of a setting, and I'm going to show a zoom in with one of our high-resolution cameras, and you can see here distinct coarser-grained cores with fine-grained drapes overlying them. And you can see the ripple crests beautifully preserved, the form sets beautifully preserved. And what we interpret these is shallow water bodies within basically interdune lenses, essentially. When we can look at the grain sizes of these nicely. And here's a close-up image. You can see the scale over there. So we can see grains in the coarser grain parts, in the cores of the ripples, which are about 200 microns. And then we see these fine, muddy drapes overlying them. So what is that we're getting episodes of coarse-grained bedload transport in waves, moving the sediment in these shallow lenses, and then we get the drop of wind activity to produce those waves, and we get fall out of suspension to produce these drapes over them. But it's just remarkable to be able to reconstruct that with the fidelity we can. And then we came across, higher up in the section, just the most spectacular example of a unit which we call the marker bed that can be traced for hundreds of tens of kilometers along the side of Mount Sharp. We call this the marker bed, and when we looked at this in detail, we can zoom in with our detailed images. This was a particular workspace we analyzed. The yellow box will show you the details. What you can see here, you've got a scale over there, 20 centimeters. You can see these resistant sandstone beds within this overall package, separated by more recessive, likely mudstones. But you can see the waviness to those resistant beds. We were able to take a picture looking front on at that face, and you can't imagine how difficult it is to do that with the rover. It's really difficult for the engineers to design this. It's very easy for the geologists to say, please take a picture of that rock. It's obviously difficult to choosing which rock to look at because there's so many, but here's a front, what we call this is a dog's eye view. That's just basically putting you down orthogonal to the rock. And you can see these beautiful rounded wave ripple crests. And this is just a slam dunk. It just tells you that this is the one example on the team where nobody disagrees. Most things, if I say, I interpret this as this, somebody will almost certainly, and usually Chris, will say, no, I don't agree with you, it's that. This was the only example I've seen on the team where absolutely 100% all the team agreed that these were clear wave ripples. I mean, of course, you will likely disagree, and hopefully the paper will come out sometime later this year. I think it's just been submitted. But you see these beautiful wave ripples suggesting that this was a standing body of water that wind blowed across and produced these ripples at the surface here spectacularly in this thing. And those wave ripples actually preserved in plan form. So you can see an example here. This is the bedding planes preserved at the top of the marker band, and you can see the ripple crests beautifully preserved, and you can basically map the ripple crests, their orientations. This is it in a rose diagram, and then work out the paleo wind direction azimuth, basically. And there's a beautiful example from one of our tomorrow's keynote speakers, actually, over here from Amise, which shows this beautiful paper from in sedimentology on lake dynamics in an early Jurassic desert, which has this beautiful Clarence Formation lacustrine that we've been using as an analog to interpret our example on Mars over here. So these Earth analogs are fantastic with basically large-scale lakes within these interdune areas. We have spectacular stratigraphy with above that wet environment, which dried up. Then we have a major unconformity called the Sicker Point unconformity, obviously named after the famous one here. And there we see a dramatic shift in environment, probably an age gap of millions of years. You can see that unconformity beautifully in this image over here. So these are lacustrine mudstones into these deposits. And struggling here. And sorry about that. Don't use your own laptop, there's a danger. And this is the Stimson Formation, which is large-scale aeolian deposits, and I hope, I can't point that side, but hopefully you can see these beautiful planar cross-sets over here that are about 1 meter tall, representing stacked dune sets. And when you look at the details, the grain size, the beautiful rounded grains suggesting a clear aeolian environment over here, so some sort of large-scale sand, sea, erg deposits over here. And because we have stereo cameras, we can, with high fidelity, measure the cross-set orientations and actually reconstruct the paleo directions. And so this just shows you the dune migration directions, much clearer in the northern part of the outcrop, directed towards the north-northeast, and much more complex as we get further to the south. But it's amazing that we can actually do this on Mars, I think. So overall, a very, very complex history of Gale crater. Early, it was interpreted as wet to dry, but actually here now we have much more complexity, as we would expect on Earth. Mars is much more complex, and we see transitions between wet to dry, back into wet again, small-scale lakes developed, a major unconformity, aeolian, but then becomes wet again. So wait on that story there. But it's building, Mars is basically changed from being a Lego planet to a real planet with enormous complexity to it. How am I doing it for time? Lots of it. Okay. Sorry? Okay, that's good. So I'm going to deal with this, tell you about the other rover. So Perseverance is the rover that launched more recently and landed successfully again. I'm very fortunate to be on the team, and actually that ended up purely by chance. There was no plan to do that. You can see a beautiful selfie of the rover. We landed in a site called Jezero crater, and again, this site was chosen for sedimentological reasons. Basically, We don't send missions to Mars to do sedimentology, but thank you, US taxpayer. But it's really about astrobiologists, search for life. And I think most planetary scientists and astrobiologists recognize that it's very unlikely that we're going to discover life on Mars by itself with a rover. We really need samples back. And so the idea was to go to this crater that was hypothesized to have held a lake and collect samples from there and return those to Earth 10 years later to analyze them in Earth laboratories to look for biosignatures, for chemical signatures for life, etc. So we landed successfully on the surface, and this is just an amazing robot, essentially, with a huge number of tools on board, complex geochemistry, an amazing number of cameras. And the key thing, however, is that it has this amazing arm to core. So Curiosity drilled and analyzed rock samples, so the rock dirt, basically, and did XRD and chemistry for organics, etc. But what Perseverance is doing is collecting rock cores for return. So within the belly of the beast, we have this very complex instrumentation. This is the sample handling facility. So we have 42 tubes in there, of which 38 are for rock or soil samples. And of those, well, we're arguing as to how many will actually be returned, but it'll probably be about the order of about 20 will be returned. Now, as all of you know, when we do field work on Earth, you have a rucksack, you collect a rock sample, you stick it in your rucksack, you carry on doing field work. If you find a better rock sample, you chuck the previous one out and put the new rock one in. We can't do that. So we have this immense difficulty, is do we sample now or do we sample later? And that's just really, really difficult. So lots of strategies have been developed. Really, at the end of the day, obviously the mission is about finding life. We don't really know where we're going to find life. There's all sorts of possibilities and guesses. We don't really know, if we're honest. And so the key thing is to sample diversity. And also, life might not have arisen on Mars. And so you don't want to collect samples that don't have, you want samples to do other things. And so our samples will also address, actually, perhaps an equal problem is, the rocks we're looking at are 3.7 billion years old. We don't have rocks of that age on Earth. We're going to get rocks that we don't have on Earth to analyze and examine in Earth laboratories. And so we basically pick different geological units and collect samples from these. But we have a difficult task of basically choosing when to collect those samples. So we landed in Jezero crater, which is a crater that was identified as having held a lake previously. So you see these beautiful landscapes. In the distance, you can see the crater rim. And this slide shows you the crater. It's about 45 kilometers in diameter. And what we can see is that there's a river valley entering the crater, Neretva Vallis, and there's a valley exiting it. So it must have held water at some point. And so we were very clear that there must have been water present. And at the margin, where the Neretva Vallis enters the crater, there's a large sediment fan developed, which clearly requires water transport in there. So the key thing was to analyze that and reconstruct the geology of that. So this is the Jezero crater western fan, or delta, if you like. And these are all the samples we collected on that traverse in a 2-year period. And we're now at that current rover position. So I'm going to talk a bit about that and what we've done. So initially, we focused our attention on the erosional scarp at the front of the fan over here. And that's where we've collected the bulk of our samples. And particularly astrobiologists are interested in fine-grained samples, mudstones and siltstones for containing organics. So that's where we focused our sampling. So you can see our traverse. It's a bit crazy because essentially we were in search mode. We didn't know where to look. We didn't know where to sample. And also we had great difficulties in sampling. Mudstones are not very easy to sample with a corer, and we experienced great difficulties in being able to do that. So it was very, very challenging, and that's why we have so many different routes and pathways, etc., and where we could get to. The landscapes and the stratigraphy is just spectacular. So here you can see this 40-meter high cliff face preserving beautiful stratigraphy, etc. So just leading through the lower part of the stratigraphy, which was what the rover could examine in situ, where we could put our arm on. Here's a stratigraphic log through that. You won't be able to see the details, but you can see the grain size changes. The lower part, again, has two different interpretations, which, again, if we had fossils, biota, we could solve immediately, but it's challenging. So the lower part of the stratigraphy, it's fine-grained mudstones, siltstones, devoid of sedimentary structures largely, apart from planar lamination. And then we get some sandstones with plain laminations or massive, structureless. And so the two different interpretations are, firstly, that these are early-stage distal fluvial deposits, distal parts of an alluvial fan. An alternative is that these are actually pro-delta deposits at the base of a delta sequence. There's nothing intrinsic to the sedimentary structures that enables you to choose between those two different interpretations. That's the complexity of doing this on Mars, is really that we can't, in all honesty, we can't really tell, because all the sedimentary structures could be formed in those different settings. It's the overall context, but even still, one has to be very wary. What gets clearer is going higher up, and so here we can see these finer grain successions, and we tried and struggled to sample this sequence and just couldn't sample it, basically, because the engineers deemed it too dangerous to sample, basically, for the drills. Essentially, they said we won't recover sample. So, unfortunately. But then, right at the top of the lower succession, we do get this beautiful light-toned deposits. You can see at the bottom over there, light-toned mudstone that can be traced for hundreds of meters, basically, along strike. I haven't actually measured it, hundreds and hundreds of meters. And that, we are very clear, likely represents a lacustrine deposit that spread across the crater. And that's been one of our clear samples, basically. And above that, we go into a coarsening up succession. So here is that sample over there of Hogwallow Flats. That's our highest priority sample for astrobiology. You can see what we do is we abrade the rock surface to remove the dust and the weathering products, and you can see it's a really fine-grained deposit. We've sampled that, and that's one of our highest priority samples to be coming back. And you can see here we are sampling it with our arm, and here's the sample in the core barrel over there, etc. And then above that succession, we go into something that we can be probably likely more sure of. There are alternative interpretations, but we go into a succession that shows high-angled inclined stratification. So this is a outcrop called Franklin Cliffs. And I'm going to show you a section right at the top of that where we see, I'll show you a few sections, this is one that I've been working on, where we see these beautiful inclined beds, basically, large-scale inclined beds that are up to 15 to 20 meters tall. So the dominant interpretation for these, and then they're truncated by an erosional surface, marked erosional surface, and we see planar laminated sandstones, pebbly sandstones overlying it. And the interpretation of these is that what we're seeing are delta topset and delta foreset deposits. The foresets, the inclined beds, always dip into the crater center. We never see dips the other way. So the alternative interpretation is that these represent some sort of fluvial bar deposits, but they're pretty big bars to produce something of that size. So, the team is arguing about that. I'm sure people in the community will argue about that. You can see the scale over here. But these represent avalanche deposits on the face of either a really, really large longitudinal bar, or they're representing delta foreset deposits. What I'm not seeing is stacked fluvial bar deposits here. We do see this single transition from the foreset into the top sets with nice boulders up to a meter in diameter across, and they look very, very similar to these beautiful examples you see from the Gulf of Corinth, the Pleistocene examples that have been well researched. Again, with our beautiful stereo imagery, we can reconstruct the 3D geometry, measure the inclinations beautifully, so they're 25-degree dipping foreset deposits over there. So My preferred interpretation of these are delta 4 set in a Gilbert-type delta, but we should be open to other interpretations. Subsequently, we drove onto the delta top, and prior to this, people had observed features that looked like meandering river deposits. I'll show you an example in a minute. Let's zoom in. Here we can see we saw some large-scale curvilinear features that looked like the plan form of meandering streams, and the interpretation prior to landing were these were meandering streams. But we got up on top of that delta top, or the fan top, I should say, and again saw cliniforms, so large-scale inclined beds up to 15 meters thick with angle of repose cross bedding. And so it's really difficult to interpret these in terms of that bar deposit or in terms of, lateral accretion features. Not saying it's slam dunk, and here the team is arguing between us as to what is the best interpretation here. We'll have a sample back, and the astrobiologists don't care what sedimentary environment it formed in. They just want the sample to see what's in the cement, what's in the pore space preserved in there. But obviously for us sedimentologists, it's really interesting to know what there is. So this is an example of a sample we collected, Melin at the Tenby. This is a Tenby formation, where we see these large-scale curved beds. And so what you can see here, you'll see this thing, you can see these large-scale curved beds in plan form. So either these are lateral accretion along strike with flow this way, but these were bar forms building sideways, or that these are very complex geometries of delta mouth bars with very complex 3D geometry building these features. And what we're seeing is basically the erosion surface is basically sliced through those foreset deposits here. People are working on that at the moment, so it's sort of developing as we speak. Oh, behave. It's telling me to dial into the JPL. And then right at the top of the succession, we see a series of nonconformities, as you'd expect in a fan with erosional surfaces. And we see these beautiful fluvial deposits, planar laminated sandstones, likely upper stage bed forms, overlain by these boulder deposits, which have formed a lag over the top. And so the fan deposits represent these are the later stage fan deposits with upper stage flow fluvial sandstones, and then we have a later event, probably an unconformity that we couldn't map in the field, where we see these boulder deposits that we interpret, and the boulder is up to 2 meters in diameter, rounded boulders. We've tried to sample the boulders, but they're really, really hard, so we didn't want to risk it, but they're likely to represent some sort of outflow flood deposits, basically, that completely covered the surface of that sediment fan. And finally, we're examining what was called the margin unit, and this is really intriguing because from orbit it showed a strong carbonate signature. We've not analyzed carbonates on Mars before, so this is one of the reasons that Jezero was chosen. And the interpretation of this was it basically forms a carbonate signature in the orbital spectroscopy, and it forms a bathtub ring around the inner edge of the crater. So one of the hypotheses for these was this was a shoreline deposit, a carbonate shoreline deposit. We've got there, and it's been really puzzling. So when we first got there to the edge, we actually found sandstones. So we can see these sandstones. This is a close-up image. You can see a moderately well-sorted sandstone with carbonate grains and silica grains. So we thought, gosh, this is amazing. We've got some sort of shallow marine deposit. But then we drove further, and we just got massive beds of carbonate-rich lithologies, but no sedimentary structures whatsoever. Nothing. They're just massive. So at the moment, the team is arguing as to whether these are sedimentary or igneous. It's that fundamental. We can't tell. And it's quite a heated debate on the team, but we just can't tell. Even the close-up images, when we abrade and look at an unweathered surface, we still can't tell. not quite clear whether these are grains or whether they're crystals that are interlocking or whatever. So I suspect that we're going to have to wait till we get back. For me, as a sedimentologist, I've been arguing it's igneous because I just don't see any sedimentary structures whatsoever. And I would expect in a grainstone of this sort some sort of cross-bedding, something like some sort of lamination. They are layered, but you see layering in igneous lava flows, etc. So we don't know whether it's an ash bed of some sort, etc. So here, we really need the samples back to actually tell what those rocks are, because we don't really know. So what I'd like to leave you with is, just really diverse environments in Jezero Crater, really exciting in terms of different sedimentological settings. And it's actually amazing, I think, to think what we can actually do with a rover with our fasces-based traditional sedimentology in reconstructing that past and that sedimentary evolution. And these are the samples we're going to bring back. So the crater floor samples are actually lava flows, igneous. And we have a radar, ground-penetrating radar on board, and it's actually shown that the delta deposits actually, or the fan deposits actually overlie these lava flows. We have collected samples from the lava flows, and we're going to be able to date those in Earth laboratories. So we're going to get the age of when that fan initiated. We'll have lots of detrital minerals within those samples that we collected. So you could see all our fan samples over here. They have lots of detrital minerals, and we should be able to date those samples when they come back to Earth. So we will be able to reconstruct an approximate chronology for these and the provenance history from these samples too. So not only do we have the paleo environments and the evolution, but also the provenance history, how the catchment has evolved, and that source-to-sink story from overall from these samples. And finally, who knows what those samples might yield? But here's a little bit of graffiti from my neighborhood. Who knows whether those samples will yield us evidence for past life. Thank you very much.
Yeah, thank you, Sanjeev. I think we're very lucky that the rover's more reliable than your laptop.
That's right.
You were able to show us those amazing images. Do we have any questions for Sanjeev? Alex at the front. I'll repeat it probably.
Yeah, so one of the last images you showed, that carbonates, igneous potential stuff. What tests would you do when you get the sample back to show whether it's igneous or sedimentary? Will it be possible to tell with a sample?
I think sticking it into some sort of microscope to look at the texture, basically. I think it's a textural thing, and we can't actually see the texture at the moment. So it's, what we can't do is even if we don't understand something, we can't carry on looking because we've got other stuff to go to. And so we might have been able to solve it. We've done 3 abrasions. The first 2 abrasions showed a sedimentary signature, but the subsequent abrasion, or subsequent 2 abrasions, so we've done 4 abrasions, we just can't tell the texture. So it's really the textural information that will tell us, sticking it into a microscope. The thing that's fundamental for geologists on Earth is a thin section. We can't do thin sections, and that's really makes things difficult.
We have another question. We also have a microphone, so just
there's one over here as well. Hi, thanks, Sanjeev. Quick question. The different gravitational acceleration on Mars and bed forms. What has been done to consider that?
So I think lots of people on Earth have sort of looked at that scaling stuff, etc., and it seems to make not much difference in terms of bed forms themselves. It's different in terms of your settling velocities and your transport rates, etc. There's a nice paper that's just come out recently. But in terms of the type of bed form, I think somebody should look at that. I haven't really looked at that, but I've not been surprised by anything that we've seen in terms of the bed form types, basically. So get a nice angle of repose, cross-bedding, exactly what we would see on Earth. The dune scale cross-stratification looks very similar to what we would see in aeolian dune deposits, etc. So, yeah.
There is a Mars chamber if you want to do experiments. There's a Mars chamber.
Yeah.
Okay, my question would be on the point you made that you have developed a lot of strategies for sampling on Mars. So can any of those strategies or lessons be used in remote areas on Earth? Because usually we apply the other way around. What we learned on Earth, we try to look how it works on other planets. But how about the other way around?
I think our situation is so extreme that it wouldn't really be. I mean, we're really, if you stay too long in one place, you're going to miss something else. There's always gold tomorrow, basically. And so we just have to be really, really harsh in what we can do. And I think we would never have those extreme cases on Earth, basically. But I think what we do have is, you know, because we work with engineers, they have a lot of systems engineering in how you do things. And I think some of those tools and the way you plan expeditions, plan your strategy could be. I kind of try and teach students now in the field in a more sort of checklist, more do this way, rather than when I was taught it was just a bit random, go and look at stuff randomly. We now sort of employ ways, you know, strategies of how you would go about analyzing an outcrop. So I teach students in a much more strategic way of how to look at sedimentary rocks that I've developed from how we do it on Mars that we wouldn't have done in the past. You can't, when you get to an outcrop, like a quarry or something, you kind of just say, go and have a look and see what you can discover. But actually, that's not a good learning way, and I think it's better to teach them more systematic. First do this, now do this. Make a decision. So actually, the other thing I'm teaching, we have to make a lot of decisions, so we make a lot of decision trees, because any fork has a lot of consequences. So just imagine that each day on Mars probably costs hundreds of thousands of dollars per day. So you don't waste any time. You can't sit around and think about things. So you're kind of beholden to the taxpayer, basically, of not wasting time. So we have clearly developed strategies of, if we do this, what is the cost? We do it in terms of day cost rather than financial cost, but there's a financial cost to the days. It would be nice to go and look at that outcrop where Will is sitting, but it's going to take us several days to go there. We might solve the problem, but we might not. But it's going to cost us 5 times more than looking at a rock down here. And so that's the sort of strategy. And I think I teach students more in terms of how do we make decisions. And I think that's quite a useful skill to teach, in addition to just the basic sedimentology. There was a question there.
A couple more questions. We've got a microphone. You go first.
Yes, thank you very much. So that's really beautiful. It actually reminded me of Precambrian fluviatile sediments I've seen in the desert of Oman. So there comes my question. So we have this relatively short-lived wet period of Mars. I presume that's the point of view. It's relatively short-lived. And do we have evidence that there was a prolonged desert stage after that? I mean, density of atmosphere, desert pavement, wind erosion, and so on and so forth. Do we see that?
Yeah, so the paradigm for Mars has always been that it was wet early and then dried up. And that's really from the orbital signature. So what you see in the orbital signatures in the oldest rocks. So Mars doesn't have plate tectonics. So what people do is the surface has always been there. So people count craters, crater density, as a signature of age of the surface, basically. So the southern highlands of Mars are heavily cratered, and so they're thought to be the oldest rocks. And that's where we see clay mineral signatures, so water-rock interaction. And in the more younger rocks, you don't see any hydration, no hydration signature. As we've seen from the rovers, the story is much more complex, but in general, it's thought that after about 3 billion years, Mars had lost its water, and there's certainly no evidence for water. The atmospheric density doesn't support water at the present day. There are gullies that might be brine formed, but they're very small scale. So certainly about 3 billion years, Mars lost its water. Remember, it's a much smaller planet than Earth, so it cooled much more quickly than Earth. So there is that overall signature of drying out, but the details of that are not very clear, and it's much more complex than people imagined. And so there may be many more places to look for evidence for life than previously thought.
Time for one more?
Yeah. Thank you very much, Sanjeev. Very great presentation. Lots of sedimentary phenomena. but unfortunately, I'm an organic geochemist. So my quick question is, which site do you think has the most potential to contain body fossils like fishes, or if not, probably molecular fossils like biomarkers, Stearns or Hopkins, because I am an organic geochemist.
Yeah. Okay, so firstly, curiosity has discovered organics. So in that, when we first got to the lake deposits, actually right early in the stages, early in the mission, we've analyzed the samples, the mudstone samples, in an instrument called SAM, Sample Analysis of Mars, which basically is gas chromatography. And it's discovered moderately complex organics that are the breakdown products of more complex organics, but it is thought that those organics are abiotic and were likely delivered to the Martian surface by meteorites. But it is amazing that you can discover organics on Mars in 3.5 billion-year-old mudstone. So I think that's a win. And I think there's a couple of papers about to come out with more. In Glen Torridon, we've got even more organics. That's just turned out to be a bonanza, etc. So some people argue maybe we should have gone back to Gale Crater for the sample return mission. With Jezero, I think we've been a little bit disappointed we didn't discover the abundance of mudstones in the crater deposits. We have some, so we have those samples. But who knows? You know, we have some really nice examples of microbial mats from South Africa, which are in sandstones. There's been some nice papers on that. So we don't really know exactly where to look for. So I think we're just going to have to get these samples back. You know, we might have samples within these, might have organics within these lava flows. And then next step for the mission is to go out to what we call the crater rim, where we have lots of evidence for ancient hydrothermal activity. So there might be samples associated with that. And then we go out, we will hopefully go out of the crater into rocks beyond the crater, and those are rocks that are about 4 billion years old. We simply have no idea what those rocks are. And again, who knows what's in those rocks? So I think it's a matter of exploration. It's a little bit difficult to be entirely predictive about these things, and I think we just have to see what we find.
Thank you.
Yeah, fantastic talk and answers. In an effort to keep on time, we'll have to draw it to a close there, but I think let's thank Sanjeev one more time.
Thank you very much.